it takes a little bit longer, but it could mean a lot for the client as far as material and installation costs to do this additional check based on two directions of the load. All right, so this is following up what Stuart mentioned last week about the positive versus negative anchor analysis. When designing strap type of anchorage, especially like typically at the head, the load direction needs to be considered. Typically the reactions from negative suction wind pressure are much higher than those from positive wind pressure, and as such, material and installation cost can be prevented with a quick check in both directions. So on the back of that page, you see the design pressures for a cornerstone frame. The cornerstone pressure is about twice as much as a non-cornerstone pressure. So you have a 27.7 psi for the positive pressure, and then 50.9 for the negative pressure. So I included the RISA model of this one window frame that shows the maximum head reaction of 362 pounds. This reaction comes from the negative suction wind load pressure. And on the next sheet, what I've done is I said, okay, that 362 pounds from suction is going to be causing that diagram of moments and reactions as shown there. So I resolved the moment about that point, that overturning point, and then I used RISA model to, well actually on this one I didn't use my RISA model, I just did statics to find what my R1 and R2 were on those clips that are grabbing that head receptor. That point 1 and point 2 on that sketch, those 2 points are what are holding the strap to the head receptor. So I resolved the loads, those R1s and R2s, due to the overturning moment that the negative 360 pounds was causing. And then I used those two R1 and R2 forces on a RISA model to come up with what that moment was due to those loads. One thing that Stuart mentioned is that we can assume that the strap anchor at the very at the left end of that figure up there is going to be seeing kind of like a point support thanks to that shim. That's why we typically assume a non-compressible shim. So it would be safe to assume that at that left end point you have like a point support. So on the RISA model you could see that on that left support location being kind of like a point support. Then you go on and apply those loads, those 480 pound loads on your RISA model and come up with that moment of 34.9 foot-pounds of critical moment. The aluminum design manual in section F4, they have equations for bending for both yielding and rupture of an aluminum part. Manipulating that equation a little bit, breaking down that Z, that polar moment and that SX into BT and like the width and the thickness of the strap, you could come up with an equation that tells you what is the width required for that 3/16 inch strap on the top. So you come up with a required width of the strap of about 3.6 for yielding and 3.27 for rupture. In this case, the client was using a 6-inch strap on the head of these frames. There were some and this lesson learned came because we were calling out a 9-inch strap at the head because we considered the worst case load on the other direction. So if you turn into the last page, you could reduce that 362 pounds due to the positive wind, and it comes down to 198 pounds. And the bending on that strap is a little bit worse, like the eccentricity and the load transfer to that strap has a more critical eccentricity and load path for this smaller load. However, doing the same be required analysis, you come up with a strap that is about 3.9 inches for yielding and 3.5 inches for rupture. And what I was saying before is that we being conservatively, we applied a 362 pound load on that direction and came up with a strap width required for that load, which was closer to like 7.5. And then we had to add some edge distance on each side, so we were calling out a 9-inch strap at the head. The client ran out of those 9-inch straps, and they installed some 6-inch straps at the head. So they asked us if we could look at this closer and see if we could come up with, do some magic, like our client was saying, to find a way that the 6-inch straps would work. So after talking with Stuart and kind of resolving this in a 2-direction type of load, we found out that yes, in fact, the 6-inch strap was sufficient for all the head receptors. So, like Stuart was saying yesterday, always try to. It doesn't. I mean, it takes a little bit longer, but it could mean a lot for the client as far as material and installation costs to do this additional check based on 2 directions of the load. And this also has a big impact on edge distances in concrete whenever you apply the load in one direction versus the other.
Question on this is just on the analysis of this.
Yeah.
So the way that you have the basically compression at R1 and then tension at R2.
Mm-hmm.
Is that correct? So if we have this point of rotation out at the very left side,
It's at the sealant.
what?
It's at the sealant. That's not where the fulcrum is. Is that where you're getting at?
So yeah, what I was saying, if you do have rotation out about that top left point, you're not going to have compression, a tension couple. You're going to have small tension here, larger tension out here.
Yeah, this can't be a
So
compression.
this is the rotation point. Isn't
Yeah,
it?
Yeah.
it's just
Well,
moved into
real fulcrum
where
is
it's
actually
forcing that up.
On the other.
But it's not about a point of rotation. It's just simply a moment applied. We're not saying that it's
Okay,
rotating
so
about that.
Okay,
It's just
all right.
due to
okay.
the 360 and that
Gotcha.
1.6 and eccentricity, there's
Yeah.
a moment
Okay.
at that bend. So it's rotating
Makes sense.
about
Makes
one-
sense. I
Yeah.
thought that you were using the point of rotation there to figure
Oh
out.
no,
Okay.
no. It
Okay.
was just
Yep.
applying that moment there, and then just doing your free body diagram to come
Yeah.
up with those
Yep.
R1 and R2.
Okay.
So this took me maybe 20 minutes extra to do, like the run that, the RISA model, and come, well, maybe half an hour. But that could save the client a ton of headache. You know, they could use the exact same strap width everywhere without having to worry about 2 or 3 different strap widths.
Question about your recent model.
Mhm.
At the screw head, did you fix a moment at that point? Is that why that curve goes to 0 right at the screw?
No, I think I just added a constraint on the X for rotation, for stability of it. It wasn't like having just an X and Y constraint. But there's no restraint against moment on Z. But there wouldn't be any moment to the right of it.
Well, that's why I'm wondering, because if in some cases you can end up with bending in that cantilever that's on 2 inches to the right of the screw, that can add prying to that. And if you model it in RISA with like a spring on that far node, it'll pick up on that. And it can mess with
Oh, on the right end of the strap?
Right. Because the way the moment curve on this is looking, it looks like there's a fixed point at that screw, but it may not be. Just another thing to watch out for, because everything on that right 2 inches from the screw is actually going to be buried on something.
Yeah.
So
But
yeah,
wouldn't it
if it's
stop
a-
there though? Like the moment would die basically at that fast?
Not necessarily. Depending on where you put your springs, you can end up with kind of a wavy moment curve along that cantilever.
Yeah, that's actually a very good point, that it acts as another prying area where you have,
All right.
Yeah, at the
Yeah.
far right, it could act as another prying area where, you know, it could receive, if it was free to rotate and there was nothing there, it would have a degree of rotation. It would actually move in the upward direction.
And your moment curve will look more like a kind of a multi-span curtain wall where you end up with that peak across your wood anchors.
Yeah. But ultimately, this should be conservative because it's actually,
It's not accounting for that
it's not
barrier
accounting
surface
for
in the
that,
back.
so it's, yeah.
Yeah. Now, and one assumption that we're making here too is that the thermal strut can take that, can be continuous. On the previous page from that thermal break, we're assuming that should be as rigid as the aluminum and kind of transferring that R1. Which-
The shear across the thermal.
Yeah, which I'm not sure how we would even model it not being continuous. I guess. I mean, there's been testing.
Yeah,
Azon provides the PVC material for this, and I think they have values for their.
For a shear being
Properties.
carried across it, I'm all right. As far as rotation, you know, that's where it gets tricky, you know, whether it can, you know, carry bending moment is a different matter. So in this case, it doesn't rely on bending moment associated with the receptor piece. It just relies on shear being transferred across the thermal break.